Welcome to monotonic sequences. So quick definition, a sequence A sub n is said to be monotonically increasing if the sequence never shrinks. So if A sub n plus 1 is greater than or equal to A sub n for all n. And so the sequence never gets, the values never get smaller at any point in the sequence. Similarly, sequence A sub n is said to be monotonically decreasing if the values never get larger. So if A sub n plus 1 is less than or equal to A sub n for all n. So as we work our way through the sequence, the values either stay the same or get smaller. They never get larger. That's monotonically decreasing. So let's, for example, determine whether each of the following sequences is monotonically increasing, monotonically decreasing, or neither. So if we look at A sub n equaling n plus 1 over n squared, let's just see what happens as we work our way through the sequence. So A sub 1, we would be looking at 1 plus 1 over 1 squared, which is 2. A sub 2, we would be looking at 2 plus 1 over 2 squared, which is 3/4. A sub 3, we would have 3 plus 1 over 3 squared, which is 4/9. A sub 4, we would have 4 plus 1 over 4 squared equals 5/16. And it certainly appears to be monotonically decreasing. How can we be sure? So to be sure, what we can do is we can do A sub n plus 1 minus A sub n. If it's monotonically decreasing, A sub n plus 1 minus A sub n should be less than or equal to 0, since A sub n plus 1 should be less than or equal to A sub n. So we have A sub n plus 1 would be n plus 1 plus 1 over n plus 1 squared. Then we subtract off A sub n, which is n plus 1 over n squared. We want to know, is this less than or equal to 0? Or we can actually just check if one is less than or equal to the other, right? If the A sub n plus 1 is less than or equal to A sub n. So this is equivalent to saying n squared times n plus 2 is less than or equal to n plus 1 cubed. This is n cubed plus 2n squared versus n cubed plus 3n squared plus 3n plus 1. And that definitely is a less than or equal to, so we do hold out. So next up, let's take a look at b sub n equaling, let's take a look at b sub n equals n factorial over 3 to the n. So again, let's check b sub n plus 1 minus b sub n and see what we're looking at. So b sub n plus 1 would be n plus 1 factorial over 3 to the n plus 1. We are subtracting off b sub n, which would be n factorial over 3 to the n. If we just multiply that second fraction by 3 over 3, we'll have n plus 1 factorial minus 3n factorial all over 3 to the n plus 1. And we want to know, how does this compare to 0? So at n equals 2, b sub n plus 1 minus b sub n equals 0. For n greater than 2, b sub n plus 1 minus b sub n would be positive. But what happens at n equals 1? At n equals 1, we would have 2 factorial minus 3 times 1 factorial all over 3 squared. And this will wind up being less than 0. So since we have some less than and some greater than, this is not monotonic. So this is neither, it's just not monotonic. So as soon as we get past n equals 1, it becomes a monotonically increasing sequence. But unfortunately, because of that n equals 1, it is not monotonic. So a quick theorem. If the sequence a sub n is monotonically increasing, and bounded above, then a sub n converges. So essentially, the function is maybe always going up a little, but it reaches a point it can't go any further past, and it can't go back down, so it has to converge. Right. Similarly, if a sub n is monotonically decreasing and bounded below, then a sub n converges. And so again, essentially, we have bounded above, we have a line that cannot be crossed above. And if we have a function that's increasing along the way, it must never go past that, can't go back down, it has to limit. Similarly, if we have something bounded below, if it's monotonically decreasing, we're heading downward, 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 and it can never pass the line, so we must have our limit. it must converge. So this again is a useful trick for checking if something converges or diverges. If we can tell it's got this constantly increasing but can't go above something, or constantly decreasing but can't go below, we know it converges. Just a quick side note. Just a note. These both hold even if they're just eventually monotonic and eventually bounded. So these both hold even if they are just eventually monotonic and eventually bounded. Again, convergence deals specifically with what's happening for large N. So we can kind of ignore what's happening at the beginning of our sequence and just pay attention to what's happening at the end. So if we have a case like our second example, where from n equals 1 to n equals 2, we actually drop, but then beyond that, it's monotonically increasing. If it's bounded above, we would have a convergent series. So again, just something to pay attention to and to watch out for. That even though the theorem states that it's just flat out monotonically increasing or decreasing, the theorems for convergence do apply as long as it's eventually monotonically increasing and bounded above, or eventually monotonically decreasing and bounded below. Again, we don't actually need eventually when we refer to bounded, because if it is bounded, it's only eventually bounded if it's bounded, right? So we could just change that to bounded. We don't need the eventually there. All right, so that's sequences in a nutshell. Gives us something to work with once we move on to series, which will sort of come from sequences.